So far in this chapter, we have understood a few basic concepts. We understood that temperature is that property of an object which tells us the direction in which heat will flow to or from the object, from the surroundings or to the surroundings. We understood the concept of specific heat, which is that if you have an object and it is being given a certain amount of thermal energy, how much will its temperature change in response to the change in thermal energy. Now we are going to understand the concept of calorimetry or the method of calorimetry, which is a process by which we are able to figure out the heat content in a given sample of material. So what is calorimetry? A calorimeter is a device which allows us to measure the heat content of a given material with respect to some kind of a reference material. The material that we use as reference here is water. It remains liquid for a wide range of temperature. It has a fairly high specific heat capacity as well, and it is not corrosive or reactive with any material to any particular degree. So what we have here is the schematic diagram of a calorimeter. As you can see, it is essentially a box. Now, the outer layer of this box is made from some kind of insulating material. Usually it is wood. And inside this, there is a layer of high quality insulator. It can be glass wool, it can be ceramic. It is some material which has a very low conductivity. And inside that, we have a second container. And in this case, the container is made from copper. So here we also have an inner container made of copper, which actually holds the water that we are going to use as our reference material. So let's fill it up with water. There we go. And here we have a thermometer, which will tell us the actual change in temperature based on the material and the temperature at which that material is kept inside this apparatus. So how do we use it for measuring the heat content of a material? Let's say that I have a sample of a metal. Let's say I have a sample of aluminum, which is at some particular temperature. So I take a lump of aluminum and I put it inside this container. So here is my lump of aluminum. Now, let's assume that this aluminum is at a higher temperature compared to the water. The water is kept at some standard temperature. Usually it is near about 25 degrees Celsius. And in this case, the aluminum is much hotter. Let us say that aluminum is at close to 80 degrees Celsius. Now, due to the fact that the temperature of the aluminum is higher than the temperature of the water, there will be a flow of heat, and this flow of heat is always going from high temperature to low temperature. So, in other words, this piece of aluminum, this mass of aluminum is going to lose heat energy, and that energy is being gained by the water and the copper jacket of this calorimeter. But understand that since we have used a lot of material to insulate this calorimeter, there is going to be no flow of heat out or no flow of heat in to this device from the surroundings, which means that whatever heat energy is being lost by this sample of aluminum is being gained by the water and copper, but going nowhere else. And this makes things a lot easier for us, because what is going to happen here is that the thermometer's reading is going to increase because the temperature of the water is going to increase. And we will now see how this increase can be used to find out the heat content in this material. So let's say that we have aluminum, which is having a mass M1. And let's say that the specific heat of aluminum per unit mass is given as small s subscript Al. And it is at some particular temperature. Let us say it is at a temperature of, say, 85 degrees. So the temperature of the aluminum, that is T aluminum, is 85 degrees Celsius. The water is at a separate temperature. The temperature of the water is 25 degrees Celsius. We place this sample of aluminum into the water. Since the aluminum is much hotter than the water, it is going to transmit heat energy to the water, and as a result, there will be a change in the temperature of the aluminum. Let us say that the change in the temperature, so let's say that the aluminum goes from 85 degrees to something like 45 degrees. So in this case, delta T1, that is the change in the temperature of the metal sample, is equal to its initial temperature, that is 85 degrees Celsius, minus the final temperature, that is 45 degrees Celsius. This means that delta T1, that is the change in temperature, is equal to 40 degrees Celsius. We understand that when a material is losing heat energy, its temperature goes down. and this energy is being gained by the surroundings. So how do we find out the temperature lost by the aluminum? Well, that would be equal to M1 multiplied by the specific heat of aluminum, that is SAL, multiplied by its change in temperature, that is delta T1. So this tells us how much energy is being lost by the aluminum due to being at a higher temperature compared to the water. Now, we have a predetermined amount of water already sitting inside the calorimeter. Let's say the mass of this water is equal to M2, and let's say that it is also having a specific heat per unit mass equal to small s subscript W. Also, it is undergoing a change in temperature. Let's say that it is gaining heat energy from the aluminum, which means its temperature is going to rise. Let's say that the temperature change was going from 25 degrees Celsius to 40 degrees Celsius. Let's say this is equal to delta T2, and this is equal to 40 degrees Celsius minus 25 degrees Celsius. That gives us 15 degrees Celsius. So the temperature change delta T2 in this case is 15 degrees Celsius. We need to know how much heat energy has been acquired here, and this heat energy has gone not just into the water, it has also gone into the copper, because at equilibrium both copper and the water inside this calorimeter will be at the same temperature. So whatever heat is being lost by the aluminum was gained both by the water and by the copper. So we can say that on one side we have a mass of aluminum, that is M1, we have a mass of water on the other side, that is M2, and we also have a mass of copper, and it has a specific heat equal to small s Cu subscript, and it is also undergoing the same temperature change, that is 15 degrees Celsius. So in order to find out what is the energy lost by the piece of aluminum, we need to equate these terms, that is the total heat lost by the aluminum is equal to the total heat gained by this system containing water and copper. Now you can ask, sir, whether we will also consider the rest of this calorimeter in the calculation, and the truth is that the conductivity of the insulating material is so low, it undergoes a negligible change in temperature because it is a very good insulator and insulators don't conduct heat very well. As a result, we can safely neglect the heat gained by the insulating layer around the calorimeter. So equating these two sides, we get a new equation. In other words, the heat lost by the aluminum is equal to the total heat energy gained by the water and the copper jacket. Mathematically, we can say that the amount of heat energy lost by aluminum, that is equal to M1 multiplied by specific heat of aluminum multiplied by the change in the temperature of the aluminum, that is delta T1, is equal to the amount of heat gained by the mass of water and the copper jacket of the calorimeter, that is equal to M2 multiplied by SW, that is the specific heat of water, plus M3, that is the mass of the copper, multiplied by S subscript Cu, that is the specific heat per unit mass of the copper, collectively multiplied by the change in the temperature of the calorimeter system. So if we know the mass of the aluminum, the change in temperature, the mass of the water and the copper and their specific heat capacities, we can calculate the specific heat of aluminum. We can also calculate the heat content of any given substance based on the temperature change of the predetermined amount of water and copper.
Manorama Horizon. Learning made simple.